In this video, we're going to derive some of the properties of the least squares estimate of the intercept in the regression model. So first of all, we write down the expression for the intercept, which is alpha hat equals y bar minus beta hat x bar. We can write y bar as 1 over n times the sum of y. We subtract from that beta hat x bar. Now again, we can write the sum of y as n times alpha plus beta times the sum of xi plus the sum of ui, which gives us the expression shown here. Now we can simplify this to write it as alpha plus beta x bar plus the sum of ui divided by n minus beta x bar, which in turn can be written as alpha plus x bar multiplied by beta minus beta hat plus the sum of ui over n. Now we can take expectations. First note that the expected value of beta hat is equal to beta, since we've already shown that the slope coefficient's estimate is unbiased. The expected value of ui is equal to 0 for all values of i. Therefore, if we take expectations of alpha hat, the second two terms drop out and we're left with alpha. In other words, the OLS estimate of the intercept is unbiased. We want to derive an expression for the variance of the intercept. We have the variance of alpha hat is equal to the expected value of alpha hat minus its expected value squared. We've already derived an expression for the term in parentheses, and we can write this as the expected value of beta minus beta hat x bar plus the sum of ui over n, and then we square that expression. Well, let's expand that term in parentheses. So we can write this as x bar squared times the expected value of beta minus beta hat squared plus 1 over n squared times the expected value of the sum of ui all squared plus a cross product term, which can be written as 2 x bar over n multiplied by the expected value of beta minus beta hat multiplied by the sum of the errors, ui's. Now let's look at a bit more detail at that cross product term. We can note the following. We take the expectation of beta minus beta hat multiplied by the sum of the errors. We can substitute in for beta minus beta hat and write this as the expected value of minus the sum of xi minus x bar ui multiplied by the sum of ui's all divided by the sum of xi minus x bar squared. That in turn can be written as minus the sum of xi minus x bar divided by the sum of xi minus x bar squared, because we can take the x's outside the expectations operator here, multiplied by the expected value of ui multiplied by the sum of ui. However, if we look at the top, the numerator of this, we see that this expression must be equal to 0, since the sum of xi minus x bar is equal to 0 by definition. So this means the cross product term disappears when we take expectations. Therefore, going back to the variance of alpha hat, we've got the expected value of alpha hat minus its expected value squared is the sum of x bar squared multiplied by the variance of beta hat, or the expected value of beta minus beta hat squared, plus 1 over n squared multiplied by n sigma squared u, which is the expectation of the sum of ui squared. So we can write that as being equal to sigma squared u multiplied by 1 over n plus x bar squared divided by the sum of xi minus x bar squared. and that's the standard expression used for the variance.